Alright, in this video I want to talk about the column space a bit more, in particular how to find a basis for the column space. So finding a basis, oops, second. Okay, finding a basis for the column space of A. So the column space of A is a subspace, and I mean, how are you going to describe a subspace? Well, typically what you would do is you would find a basis for it and say that the space is the span of that basis. So we want to figure out how to find a basis for the column space of A so that we can say exactly what the column space of A looks like. So how do we do that? Well, in this video I'm going to talk about how to do that, but it's before I go into that, I want to emphasize that it is important to understand how it works, right? Like the science behind how it works, and not just what to do. All right, so let's look at a matrix in reduced row echelon form before we talk about what to do for any matrix. So let's look at an example. Find a basis for the column space of the matrix B, which is this matrix. So the first column is 1, 0, 0, 0, 0, 1, 0, 0, negative 3, 2, 0, 0, 5, negative 1, 0, 0, 0, 0, 1, 0. All right, so I see that I have 5 columns, and each column is in R4. So my column space is a subspace of R4. It's spanned by these 5 vectors, and I want to find a basis for it. Well, so I'm looking at the span of these 5 columns, and notice that I have these 2 pivot columns, right? This is the pivot column, that's a pivot column. Oh, there's a third pivot column here. Those are my pivot columns. Remember, how do I find the pivots when I have a matrix in echelon form? What you do is you just go from left to right and look at the first number that you see. So I have a 1 here, I have a 1 here, right? I have a 1 here. So those are my pivots, and those 3 columns are the corresponding pivot columns. Now notice that these pivot columns are linearly independent, right? So observe that the pivot columns are linearly independent. And we can see that just because, you know, if you had C1, 1, 0, 0, 0, plus C2, 0, 1, 0, 0, plus C3, 0, 0, 1, 0, equaling the 0 vector, what these equations will tell you, this first, if you look at the first row, right, if you look at this first equation here, that just says C1 plus 0 equals 0. So this first equation tells you that C1 is 0. And then if you look at the second equation, you get C2 is 0. And the third equation just tells you that C3 is 0. So that shows that these vectors are linearly independent. Now notice that I claim that they also span the column space. How come? Well, B, okay, so the column space of B is the span of these 5 vectors, right? And so if you can show that let's call these, let's just for simplicity call this V1, V2, V3, V4, and V5. If V3 is a combination of V1, V2, and V5, and V4 is also a linear combination of V1, V2, and V5, then that tells you that V3 and V4 are in the span of V1, V2, and V5. And again, by the general principle, the fact, I don't think there's a name for it, but there's this theorem that says that any vector in the span of V1 through V5 is therefore just in the span of V1, V2, and V5. Well, we can actually see how to write V3 and V4 as linear combinations of V1, V2, and V5, because if you look at V3, right, that's just negative 3V1 plus V2. Sorry, plus 2V2. And V4 is 5V1. Oops. V4 is 5V1 minus V2. So V3 and V4 are elements of the span of V1, V2, and V5, right? V1, V2, and V5 are themselves in the span of V1, V2, and V5. So, so the column space of B, well, by definition, this is the span of V1, V2, V3, V4, and V5. That's just by the definition, but the point is that this is equal to the span of V1, V2, and V5. Maybe there's a better way to phrase that the important thing is that the column space is the thing on the bottom. So we know by definition the column space is that, and this is equal. We see that the column space of B is equal to the span of V1, V2, and V5. So therefore, V1, V2, and V5 is the basis for the column space of B.
Are you on a video call right now?
Sorry?
Are you on a video call or something right now?
Yeah. Is it?
Okay, I can actually hear it from the desk. I was going to see if you needed headphones or anything.
Oh no.
Yeah.
No. Yeah. I'm gonna talk more quiet. Or is there?
Yeah, it sounded like it was the computer. I'm not sure, but like, it can definitely be heard. So I just wanted to make sure you knew that in case it was something important. But yeah. So.
Oh, I must have. I think I probably just put headphones here instead of my laptop, and maybe that was.
There you go.
Yeah.
Okay.
I think that was the reason.
All right.
Sorry about that. So, okay, so V1, V2, V5 is the basis for the column space of B. Right. So in general, the pivot columns, and this is a general fact, so in general, the pivot columns of a matrix in echelon form a basis for the column space of the matrix. So in general, the pivot columns, okay, if B is in reduced row echelon form, the pivot columns of B form a basis for the column space of B. Okay, but what happens if the matrix is not in reduced row echelon form? Well, okay, let's look at an example. So let's say that A is this matrix, 1, negative 2, 2, 3, 3, negative 2, 3, 4, 3, 2, 0, negative 1, 2, negative 8, 7, 11, negative 9, 2, 1, negative 8. Now it turns out that the echelon form, the reduced row echelon form, is just B. So reduced row echelon form of A is B, which is the matrix we had before. Oh, maybe I can copy and paste. Okay. Try this one more time. Right. Okay, why don't I just move it here? Let's see. There we go. This is the reduced row echelon form of A. Okay, now let's compare these two matrices. Let's call these W1, W2, W3, W4, and W5. So we want to find a basis for the span of W1 through W5. Now the important fact that we'll need for this is that the dependence relations, the linear dependence relations among V1 through V5 also hold for W1 through W5. So let's just look at an example. In other words, we saw that V3 is negative 3 V1 plus 2 V2. Well, it turns out that for the original matrix A, the same thing is true. So W3 is negative 3 W1 plus 2 W2. And so on. And it turns out, okay, so why is this true? Basically, the reason why this is true is, so suppose that, okay, so we know this is true. This says that one way to write this is negative 3 V1 plus 2 V2 minus V3 is the zero vector, right? So that means that negative 3, 2, negative 1, 0, 0, this is a solution to Bx equals 0. But the solutions to Bx equals 0 are the same as the solutions to Ax equals 0. So it is a solution to Ax equals 0. Oops. Equals 0. And since it's a solution to Ax equals 0, that means that A times that vector equals 0. So we must also have negative 3 W1 plus 2 W2 minus W3 equals 0. And that's the same as saying that W3 is negative 3W1 plus 2W2. Okay? So, so yeah. So that basically explains what's going on. And so, in particular, right, the pivot columns of B were linearly independent. And by the same reasoning, well, not by the same reasoning, but because of that, and we know that the dependence relations in B are the same as the dependence relations in A, in particular, W1, W2, and W5, this set is linearly independent. There's no non-trivial combination of these that produces the zero vector, and the reason is because if there were a non-trivial combination of those that gives the zero vector, then there would be a non-trivial combination of the V1, V2, and V3. Sorry, V1, V2, and V5 that give the zero vector. Okay. And moreover, these vectors W1, W2, and W5 span the column space of B. The column space of A, because we saw that V3 is V3 is a linear combination of V1 and V2, and V4 is a linear combination of V1 and V2, and by the fact, this fact, that the dependence relations among V1 through V5 also hold for W1 through W5, in the same way, W3 is a linear combination of W1, W2, and W4 is a linear combination of W1, W2. And so therefore, W1, W2, W5, this set is a basis for the column space of A. And that's how to find a basis for the column space of any matrix. Alright, so I know that there's a lot to kind of take in, and it would be a good idea for you to do some examples on your own. So let's just summarize, just to make sure we understand the bottom line. So suppose that B is an echelon form of A. It doesn't have to be the reduced row echelon form. It just needs to be such that you can see the pivot columns. Then the columns of A that correspond to the pivot columns of B form a basis. Right, the set of those columns is the basis for the column space of A. By the way, is the column space of A equal to the column space of B? Should I write it down? Is the column space of A equal to the column space of B? What do you think? You could pause the video and see if you can figure it out. Okay, let's go over the answer. The answer is no. How come? Because I see that B, when I have B, when I look at the last component, those are all 0. So any vector that's a linear combination of these column vectors will have to have the last component being 0. So actually none of these vectors, none of these columns of A, right? None of these columns of A have 0 as the last component. So none of these vectors are in the column space of B. So in general, row reduction does change the column space. Okay, so let's just leave this kind of as a warning. Row reduction in general changes the column space. So let's just look at an even simpler example. Let's just say that you had, 1, 2, 3, 6. So let's say that's our A, and we reduce it to this. Right? That's an echelon form. Well, the column space of A, what does that look like? It's spanned by 1, 3, and 2, 6. So here's 1, 3, and here's 2, 6. Right? So that's the column space of A. That's the column space of A. However, for B, it's spanned by 1, 0, 2, 0. So here's 1, 0, and here's 2, 0. And so the span of those vectors is this. So this is the column space of B. So they are not the same. And the column space of A is most definitely not equal to the column space of B. Which is why you can't use V1, V2, and V5 to be a basis for the column space of A. Okay. That's not going to work. But it turns out, by this important fact, maybe I'll just write an important fact to emphasize that this is the key behind how it all works. It's that the vectors that correspond to those pivots, okay, these vectors form a basis for the column space of A. Okay, and of course this isn't the only basis that works, because any subspace is going to have an infinite number of bases, but this is just one way to find a convenient basis